Like most things in life, it's not necessarily one is good, one is bad. They just have different purposes. If you want to focus light together, if you want to take a bunch of rays and get them all together, you're going to use a converging lens. If you want to take light and spread it on out, you're going to use a diverging lens. All right, and online folks, so things are crazy today. I had to use the computer in class because the connection doesn't work for the one in. My laptop's not working, so basically, I'll be controlling my computer here and the one online, and it's going to be an absolute chaos. All right, so converging lens, we call it convex because I don't really know where the word convex comes from, to be honest. Here's how you can remember the difference, though. Convex and concave. Why is it vex? I don't know. There's probably some Greek or Latin reason for that. Concave, though, if you look carefully, this is kind of like a cave. It kind of bends inward like a cave. No, thank you. So concave lenses kind of bend inward like a cave. Convex is the other one. That's literally how I remember the difference. I'm going to be strictly using the words converging and diverging. I mean, every now and then there may be an accidental mistake where I say convex or concave, but for the most part, diverging, converging, that's the terminology I'll be using for you all. So, and the clickers are still going to work. It's just going to be kind of funky. I won't be able to show you all everyone's responses, but at least I can still collect them. So the first clicker question is, kids often use magnifying glasses to focus sunlight and burn ants. What kind of lens achieves this goal? Great. Kids often use magnifying glasses. Is it running now? Yep, it's collecting responses now. What kind of lens would allow us to focus sunlight and burn ants? Silly question, but a fun one. Let's make me a bit smaller. I'm not going to wait super long for this because it's fairly straightforward. It's going to be the answer you expect. Converging, diverging lens or either. So we'll go to 1 minute, so it's in 20 more seconds. All right, in 5, 4, 3, 2, 1. All right, results say, yay, converging. Great job, everyone. Converging, the light rays come together and they burn ants. Great, fantastic, wonderful. So, at each type of lens, we have something called the focal point. Now, this is a little tricky to identify, to find. For converging lenses, really straightforward. It's where you have a bunch of rays, they come together and they focus. Makes sense, focal point. Diverging lenses, remember the light rays diverge, they spread out. So we define the focal point as if we took these spreading rays, it's as if that's where they're coming from. If you were looking at the other side of a diverging lens, your eyeball was over here, you would kind of see a dot here. It would seem like all the light is coming from that spot. For a converging lens, really straightforward. It's literally where all the light rays reach. For a diverging lens, it's a little funkier. It's if you were standing over here, you would see them all coming from there. So, it's where they seem to originate from. At the end of the day, not a huge deal as long as you know that if you see F, that's called focal point. That's as far as what you need to understand, that's what you need to understand is that where you see F is the focal point. And the distance from the middle of the lens to that spot is called the focal distance. Makes sense. It's the distance from the lens to that focal point. Now, lenses have a focal point on both sides because you notice they're symmetric. If you looked away and I flipped the lens upside down, you couldn't tell. It would look identical to you. So, focal points are actually on both sides, but They're symmetric. So there's a focal point here, there's a focal point the exact same distance on the other side. So a lot of what we're going to talk about today, basically everything, is how these lenses bend light and how we can use that for useful functions. And so towards that end, we're going to break them up into two pieces. We'll talk about the converging lens first, and then we'll talk about the diverging lens, and at the very end, we'll connect that to glasses. And if anyone wears contacts or glasses and you have that in your box, that negative 2.5 or negative 2 or negative 3, you'll get to learn where that comes from. We'll connect it. You literally will be able to calculate it given various parameters of these lenses, which I think is interesting. All right, so image formation. Image formation sounds really fancy. If you have an object, so when I say the word object, we need to define some stuff on here. The word object means literally an object, a physical thing, a physical object. Now that physical object is either making light or reflecting light. One way or the other, light rays are coming off it. These lines are light rays. And these light rays are going they're going everywhere. This thing is emitting light in all directions. This is what I'm relegated to, is drawing with the mouse, and I hate it. It's emitting light everywhere. But when we draw this, we're only going to consider a few lines. We don't need to consider all of them. We only need to consider a few lines. And these lines are going to come at the lens, and they're going to bend. They're going to bend, and they're going to bend in some nice rules that I'm going to teach you all. One of them, if it's parallel, will end up bending here, they'll bend here, whatever. Where they all converge, we started at the top of the object, and wherever they converge is where it's going to look like the top of the object is. If I put literally a screen there, that is where I will get a crisp image of what it looks like. It's not going to look like it originally did. If you notice here, the image, it's called an image because it's what's generated. It's not the reality. You can't touch it. It is smaller than the other one, and it's upside down. We're going to learn that that's a rule with converging lenses, that they take whatever an object looks like and they kind of flip it upside down and generate it over here a little bit smaller at some distance away. Real images, this is called a real image here because the light rays come together. I can literally put a screen there and see it. It will be projected on there. So the back of your eyeballs is kind of like a screen. And so everything you see, your eyeball is a lens, and your eyeball takes those light rays and they bends them such that they converge at the back of your eye. That's where all your sensors are, and so the image, the object gets projected to the back of your eye where you have a bunch of sensors. It processes it and then goes to your brain. So you can think of the back of your eye as a screen. You can think of literally a screen. The screen is where it ultimately gets portrayed, and you can see why this would be useful for your eye. You may be like, why would I want to take a big object and make a small image with it? Well, most of the things that you all are looking at right now are bigger than the back of your eyeball. So you need to take that object and shrink it to a smaller size to fit on the sensors at the back of your eyeball. That's important. When I'm looking at this thing, I can't project an object that's that big, it won't fit on the back of my eyeball. So anyway, real images, it's where the light rays converge together and give you a nice crisp image. All the light rays from the top of the object converge here, which is now the new top, but now it's down here. Virtual images. So if you notice for a diverging lens, by definition, the light rays diverge. They will never converge together. It's in the name. They diverge. They never converge. They never come together. They start here at the top of the object. It looks almost identical to this one. And then one goes this way, one goes this way, one goes this way. Those light rays will never come together. They're spreading apart. They're getting farther and farther from each other. So when we talk about an image here, we can't make an image on this side. We can't make a real image because a real image would be where they meet, but they don't meet. You can see they don't meet here. So what we imagine is all right, there's these light rays. Let's imagine there's an image that they're coming from, some object. Let's pretend like this lens doesn't exist. And let's just take these light rays and imagine that there was an object here that they were coming from. Oh, look. And so our image is what your eye perceives to be there. So if your eyeball is over here, your eyeball can take these diverging rays and converge them back so you actually get an image. Your eyeball is not going to see the object. When you look through the lens, your eyeball will not see the object. What it will instead see is your eyeball is used to light rays going away from an object, and so it'll say, huh, where's that object? Oh, there it is. It's this dinky little thing right here. This tiny little doodad. That's what my object looks like. So this diverging lens kind of tricks your eye into thinking that the object is actually this little doodad right here, this little small guy. Again, why would you want to do that? There's all sorts of reasons. In this case, it made it smaller, but it's upright. But you can take something big and make it kind of look smaller, and we'll explore some of these things. But lenses are used in conjunction with each other. Tons of uses. Cameras is obvious. Everyone's used to cameras. Your eyeball, obviously it's useful because all of you all have one, and it's useful for taking in light. If you all did not have something to bend light, you would, I don't know what it would look like, I guess. It just would not work as well. You wouldn't be able to focus light. You wouldn't be able to get a clear image. But we use these in conjunction, microscopes, all sorts of things. So, question to you all. I have a person in two different scenarios. And so here's my object. That's my object, and it's asking what kind of image. The image is the one back here. Or in the case of the eyeball, it's the one back here. What kind of image is that? Is it real or virtual? So for those online, the object is the real physical person. The image is the one right here. Is it real or is it virtual? That little, it's kind of hard to see, but there's a tiny little person that's upside down there. Is that real, virtual, or impossible to tell? All right, I'll wait till 1:10 for this one. So that's in 20 more seconds. All right, and 5, 4, 3, 2, 1. All right, it's projected on the screen, so by definition, it's real. So the key part here, I remember learning this, and I use the word learn very loosely. I remember when I was in Ural's, I was taking the other Physics 2 one, the other Physics 2 class, the one for engineers and scientists, and I remember not understanding this at all. Not real and virtual and being like, I have no idea what these things are. So, with that in mind, I get if right now you are like, I don't know what's going on. Here's what you need to take away from real and virtual images. Real images can be projected on a screen. Real images, that's kind of the punchline here. Real images can be projected on a screen. There's a screen, or a sensor, or anything. And another way to remember them is real images are where the light rays actually physically converge together. That's the two takeaways. What's the difference between real and virtual? Real is where the light rays converge together and therefore you can project it on a screen. Those two things go hand in hand. Virtual images, you can't project on a screen. If we kind of go back to that other slide and we look at our example here, these light rays do not converge anywhere. The image is on the other side. So how would you project? You can't project it. It's on the wrong side. So virtual images are also on the same side as the object. Real images are on the opposite side as well. So that's one way of doing it. All right. This should be very easy. What kind of images do the lenses in your eye generate? I realize the picture, well, I won't say anymore. Should be fairly straightforward. I have high confidence in this. What kind of image do the lenses in your eye generate? We'll go to like 45 seconds, so that's in 25 more seconds. All right, in 5, 4, 3, 2, 1. All right, so we already saw it on the last one. If we go back to that last slide, you can we already said these are real images. There's an eyeball right there. Hot diggity dog, it's real. It's exactly what you expect. Because your eyeball needs to converge the light rays. If the light rays did not converge, that's when something would be out of focus and be really blurry and fuzzy. And that's generally why people need glasses. Because the light rays are not converging at the right spot at the back of your eye. We'll talk about that later on. All right, so getting into some of the math, and let me point out, before I even mention this one, before I even mention magnification, let me just point out some things here. The distance from your object to the lens is called the object distance. The distance from the lens to your image is called the image distance. The height of your object is the height of your object. The height of your image is the height of your image. Great. So, with that in mind, there's our equation. Magnification, and it totally makes sense when you look at this equation. Magnification is take the image height and divide it by the object height. And we can make up some numbers and see how this equation makes really simple sense. Magnification, take your image height divided by your object height, and it turns out that equals the negative distance to your image over distance to the object. We're going to see why that negative is there in a second. I'll give you all a few seconds to kind of process that. Magnification is height of image over height of object, which also equals, turns out it equals the distance from your image divided by the distance of the object with a negative sign in front. One of the reasons it's negative, and negative is if you're an opposite orientation of your object. So if my object is upside down, that height, so say, let's make up some stuff here. Here's my object, there's some magical lens, and then here's my image. If I say that this is 2 meters high, and this one's a little small, let's say this one's -1 meter, my magnification would equal, and this is, oh, it's awful, -1 divided by 2, which comes out to a magnification of, clearly here, -1/2. It is half the size, makes sense mathematically, it's half the size, and it's upside down, it's negative. -1/2 means it's upside down and half the size. If I flip these numbers and my object was 1 meter, so this is the object, O, this is the image, I am not going to even attempt to write the word object and image with a mouse. If instead it was flipped, then the magnification would be 2. Magnification is just how many times bigger it is. Hopefully that makes some sense. I'm going to, fingers crossed, I'm going to try this one last time. I doubt it works, but maybe by magically updating it. Oh, shock, it doesn't work. All right, great. Whatever. I was hopeful that maybe tech God smiled upon me. But sadly they don't exist and therefore aren't very helpful. Alright. N greater than 1 means it's larger, n less than 1 means it's smaller. Here you can see it's 1/2, that means it's smaller. Absolute value. Regardless if it's positive or negative, doesn't change that. Alright. So, Pat, what is correct about the magnification in the following image? I have here a light bulb that is 0.75 meters away. Its image, projected on a screen, is 1.5 meters away. And my answers are as follows. Do I have a positive magnification with n less than 1, absolute value n less than 1? Do I have a... Oh, that doesn't make any sense. Hold on. Let me get rid of these absolute values because no, I do want the absolute values. Never mind. So do I have a positive magnification where the absolute value is less than 1? Do I have a positive magnification where the absolute value is still less than 1? Do I? Oh, what a joy. There'll be 2 correct answers here. I meant to flip these. Let's go ahead and flip them real quick. I realize now why I was terribly confused here. Let's keep the order here the same. So this is going to throw people off. Whatever. A lot of these clicker questions will just kind of be given all the technical difficulties. So let's flip some stuff. Get rid of my drawing tool. So we're going to make this one greater than 1, and we're going to make this one, there you go. Okay, now they're different. Now they're different. I'm going to actually stop, not count this one. Oh, great, good job, woo. All right, so re-answer this way that people online get sent the right picture. All right, so is it positive magnification with absolute value is less than 1? Is it positive magnification with absolute value is greater than 1? Is it negative magnification with absolute value is less than 1? Is it negative magnification with absolute value is greater than 1? Ooh. And to clarify in the picture, there's my object, it's small. There's my image, it's big. No math required. Well, you can do the math if you want to. But it's not required. That's the fun thing with this problem. You can get to the answer 2 different ways. We can math it, or we can look at it. Look at it. Either way. All right, we'll go to 1:30, so that's in 20 seconds. So that's in 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Oh my gosh, this thing works. All right. And close. So, the trick to answering this, it's upside down. So that automatically says that we have a negative magnification. It's going to be one of these. It's either C or D, one of those two. Upside down is negative. Then we look at the absolute value. Is it bigger or smaller? Ah, it's bigger. So the absolute value is bigger than 1 because it's bigger and it's upside down, so it's negative. So the answer here is, what the heck? Wow, okay, it's D. There we go. We'll go back and fix that. So, the answer here is D. Upside down, and it's bigger. All right. Now we're going to draw, how do we even draw these? So we've been seeing these rays, going through it and draw them, and there's some simple rules. They're not going to maybe look simple, but they are simple for how to actually draw these lines. I am not going to have you all draw any lines in the test, but I do need you to have a sense of which way they would go in general. So we will draw this picture on our note card when we do our note cards, and this note card will kind of have everything you need. This picture has everything that this has in words. So let's break down what's going on here. Rule number 1, that's this red ray right here with the 1 above it. It says winning rays entering parallel, so this flat line. We go parallel, so we can always draw this flat line. It hits the lens, and then it passes through the focal point on the other side. That's how we draw it every time, no matter what. If we have a converging lens, we take the line up here, a straight line, hit the lens, pass to the focal point. Line number 1. Line number 2. This is the easiest one to draw. You take a line from the top of the object and you draw it straight through the middle of the lens and it just keeps going. Doesn't get bent at all. This ray that hits the middle of the lens just is literally a straight line. And here's the fun thing, we don't need line 3. I'll explain line 3, but you don't even need it. Where the two lines converge is where the image will form. Where these two converge is where the image will form. So if two lines meet there, then all of them will meet there. But we'll go ahead and explain rule 3. Rule 3 is literally the opposite of rule 1. If you just kind of turn your head upside down, it'll look the same, which is a little tricky to do. So rule 3 says pass through the focal point on this side, hit the lens, and then go parallel. So it's the exact opposite of rule 1. Rule 1, flat through the focal point. Rule 3, through the focal point, flat. Where those lines meet is where we get a nice, sharp image, and that's where it's generated. So, what's the takeaway here? Know what this picture looks like effectively. Make certain if you are having a quiz or a test or whatever, we'll draw this on that. If you have this, you'll be good to go. You just need to know that the light rays are coming together and that you're using this rule to generate that. That's one of the key things here, is that they're coming together, and this is how we can draw them to generate that. So, there is 2 cases, which makes things a little unpleasant. If we are on the left side of the focal point, it looks exactly like what I just told you. Easy peasy. If we're on the left side of the focal point, it's exactly what I told you. If we're on the right side of the focal point, so the focal point is right here. So if our distance to the object is less than the focal distance, our thing looks different. We don't actually get a real image anymore. We don't get a real image anymore. And now, this is actually useful. This is the one case where the magnification is bigger, where we get a magnification that's actually bigger. You'll notice here, my image height is bigger. Well, I guess we had the previous case in the previous picture. But this is one of those uses where we can actually make our image, we can make an object appear bigger than it actually is. You all can hopefully think of many scenarios where you want to look at an object that's very, very tiny and want to make it appear bigger than it actually is. Microscopes, yay. Microscopes are used using this technique. You put your object in a specific spot within the focal distance, such that when you look at it with your eyeball, you're going to appear to see something that's way bigger than the reality. You're going to look at a cell, and it's going to be way bigger than the reality of how big it actually is. So, in this case, we just use our 2 rules. We go parallel through the focal point. We then go straight through the middle, and then we take those 2 rays, they diverge from each other, and where they converge, where they actually come together, is what your eye appears to see, and you get the height, you get the image there. I'm going to give you all at the end of this whole thing kind of a cheat sheet that says, if it's here, this is what happens. If it's here, this is what happens. So if this is all seeming a lot to kind of keep in your mind, there's going to be a nice little cheat sheet that kind of collapses all this together. But for the most part, converging lenses mostly make real images unless you're within the focal distance. Unless your object distance, the distance from your object to the mirror, is less than the focal point, then you get a virtual image that's bigger. And your eye can then take those rays and reconverge them and see what it actually is. You cannot project this on a screen. You cannot project this on a screen. So when you all use a microscope, you can't put a screen out here and see what the microscope is, the object, the image. You can't project that. You can only see it because your eyeball is a lens that then takes all those diverging rays and reconverges them to the screen at the back of your eye. So, anyway. All right. So, case in point, this is a great question that could easily show up in a quiz. I'll go ahead and hit play, start collecting stuff. I have an object located here, much farther than the focal point. Which way should light bend in the following image? Should it bend? A is up to the right, B is straight across, C is through 2 times the focal distance, and then D is through the focal distance, through the focal point. Which of the following correctly shows the way the light ray will bend? Will it bend up? Will it go straight? Will it bend down and pass through 2 times the focal point, or will it pass right through the focal point? This is the kind of question you can expect as far as these are called ray tracing diagrams. Rays, you trace them, and it's a diagram. And I'm optimistic that I realized other teachers just had the same problem I did, and they found a very clever workaround. Hey, great. I just realized other teachers had the same problem. They just took out the HDMI cable from the dock cam. And they used that one instead. So, good news. It's not me. It's the stuff. Bad news. I wasn't as clever as the other teachers until halfway through the lesson. But great. Now I can draw again. Yay. All right, online students. This will be better for you now. Whatever. So, great. Wonderful. Back to normality. I'll wait 5... No, it's just because I angered it. He's saying my cable here is very sensitive, so I may just have to do some finagling with it. Great. All right, so we'll wait to 25. 5, 4, 3, 2, 1. Great. Okay, so I mean, if we just go back to our picture here, if we have a parallel ray, it passes through the focal point. So let's see how we did. Fingers crossed. So we were split on D and C, and the key was just realizing it passes through the focal point here. Passes through F, not to F. Not to F. It passes through the focal point. So there you go. Now you know. If you missed it, that's okay. Now you know that it passes through the focal point, not 2 times the focal point. Fun fact for you all. I don't know if this matters to you. These lenses are actually, if you kind of take this curvature, it's as if we took a piece of glass from a sphere, and the center of the sphere is 2 times the focal point. So it's kind of just a fun thing. If you continued this curvature around, it would make a perfect sphere. And at the center of this perfect sphere is 2 times the focal point. Half that is the focal point. You don't need to know that, but it's fun to know. So the answer here, though, this you do need to know. That is the correct ray. Light goes parallel and then passes through the focal point. All right. Moving to grouping. Diverging lenses. So we've seen this. The light rays diverge. We have different rules here. Again, the beauty of this is the picture shows everything I'm about to describe. So rule number 1 says I have a ray going parallel. And it doesn't pass through the focal point. It can't. It diverges. But how do we know how much it diverges? Well, if we make that a straight line, that passes through the focal point. So the first one still it doesn't technically pass through, but it's as if it's passing through on the other side. So these dotted lines are not actual light rays. So we draw it, and then we draw one shooting up, where that one we just draw a straight line through the focal point. Okay? So that's our first ray. Our second ray is the easy one. We love the second one. The second one says if I have a light ray going through the center, it just keeps going. Just like the last one. If you're going right through the middle, it just keeps going right through the middle. No bending. Easy. Easy peasy. So this second one just cruising straight through the middle, no problem. Number 3, we want to make a line. Our goal for number 3 is we start here, and we want to draw a straight line to the focal point on this side. We start drawing that line, heading in the direction of that focal point on the other side. So we're heading towards that focal point, trying to hit it. But the second we hit that second we hit that lens, we go flat. So we're heading towards the focal point on the other side. We hit the lens and go flat. Okay? So I'm going to erase all this because it makes it honestly harder to see. So first one, we go flat. And then we bend upwards such that the line kind of intersects with the focal point on the same side. 2, straight through. 3, we go towards the focal point on the other side, hit the lens, and go flat. Okay. Great news. This one only has one case. It always does the same thing. It always makes an image that is virtual and right side up. Always. Virtual, meaning it's on the same side. It's not real. You can't project it on a screen. The light rays always converge. Who cares where the object is? It will always do this. It will always do this. It will always generate an image on the same side with, I believe, a smaller magnification, but I need to fact check myself on that. It always makes it smaller. Always virtual, always right side up. No matter where you are, whether you're close, whether your object is inside the focal point or outside the focal point. Always virtual, always right side up. All right. So let's go back to this, just remind ourselves, because I'm going to give you another quick. First one goes up flat, and then it's as if it passes, and then it swings upwards such that it passes the focal point, straight through the middle, and then down and flat. Let's see how we do on this. Wow, that is not in the right spot. Let's, there you go. And this answer is actually very, I won't give you hints. I was just going to say, this one's an easier one than the last one. I have a light ray going parallel. A is pointed up, B is pointed flat, C, the light rays are the same as the last one. C is pointed through the second some point that's 2 focal points away, and point D is passing through the focal point. Which of these shows which way the light ray will bend? All right, we'll go to 130 on this. All right, and 5, 4, 3, 2, 1. This one was nice and simple because there's only one ray that diverges here. There's only one ray that spreads outwards. It's A. We'll make it purple because that's what my pit is. Yay, good job, us. So, takeaways here. Divergent rays diverge. Divergent lenses diverge. Converging rays, if you're outside the focal point, they like to converge at the, if you have some straight lines, they converge at the focal point. So that's kind of the differences between these. So now that we've learned about both types of lenses, this is kind of a repeat, but just to see if you remember it. What kind of lens does your eye use? What kind of lens does your eye use? Convex or concave? Won't wait too long on this one. We'll go to 40 seconds. Yeah, maybe a little longer. We'll go to 45. And 5, 4, 3, 2, 1. So everybody asked this question. But here I use convex and concave instead of divergent and convergent. Again, good news for you all, test quiz, it'll all be convergent, divergent. Convex here is this one. Concave is the one that's got caves. So we've already talked about, we've already said this, eyeballs use converging because you need to make that real image to project in the back of your eye. We already said all that. But just kind of threw it out there again to remind us of this, now that we've talked about them all and introduced a bunch of things. Because we're going to start talking about the eyeball. And I guess we're not going to get to the math today, but that's perfectly fine. So we are going to get to the eyeball before we get to more math. So your eyeball is a converging lens. This is what the lens looks like. It looks like a converging lens. It's got that kind of teardrop shape to it. I don't know if you call that teardrop. I don't know what to call this shape, but I'm going to call it teardrop. No, it's not quite a teardrop. Oval? Oval. All right. This does project an image to the back of your eye. This image is upside down, and then your brain interprets it, Your brain's smart and knows that the world's not upside down and that people aren't walking on ceilings and all that jazz. But it does project the image to the back of your eye. The cornea does do actually a significant amount of the bending, even though it's not quite as nice of a diverging lens. It doesn't quite as look like one, but it does behave very much the same. So the cornea is here in the front, and then you have your lens. The lens does the fine-tuning. Because here's the problem. Every time we've been drawing an object, and we draw a converging lens, we need the image to always, so say I have an object here, say I have an object here, I need all of them to converge back here, at the back of the eye, regardless of their distance. So your eye is constantly changing its focal point to make this happen. The lens is constantly, there's these muscles that are stretching it or not stretching it to change it such that wherever you're looking, whatever you're focused on, that's where the word focus, focal point, whatever you're focused on, that it generates the image. And whatever one it generates the image of is going to be nice and crisp. Everything else will be slightly blurry. So you all are experiencing this right now. You're looking at me on the stage, maybe, or the screen or something. You're looking at something, unless your eyes are closed and you're asleep, in which case, enjoy your nap. Everything else, if you all just kind of notice, is slightly blurry. It's slightly blurry. So, for example, this, let's say this is me. You all are looking at me, and then let's say that there's an apple kind of behind me. Your all's lens is going to do such that it focuses, and I'll even draw all the beautiful rays now that I have my computer working. So it's going to draw those rays such that you get a little me upside down hitting the back of your eye. Yay, my arms are up, which is not what's happening there. So it's going to look identical. There you go. There's a little me at the back of your eye. That apple, though, that image is going to be, let's draw that one. That one's going to go and then right through the focal point as well. But this apple, its image is going to be behind the eye. It's not going to be in focus. Notice these two rays. This was the apple ray. This was, let's draw them green. It's a green, I'll do red. It's a red apple. So here's my red apple. So here's light ray 1. It goes like that. It passes through the focal point. And then the other one passes right through the center. Notice these two red lines do not converge here, which means they're out of focus. It's going to look fuzzy. A crisp image is where those lines come together. Where does that image actually generated for that apple? Back here, behind the eye, which is not where your sensors are, so it's not very useful. So when you all are focusing on something, your lens is modifying so that the light rays converge together for that object at the back of your eye. And your eye is constantly changing that. When you look at something close, it has to modify it. When you look at something far, it has to modify it. And when you have, I'm going to say when you, like myself, I wear contacts. If your eye doesn't do it perfectly, then you're going to get fuzzy images. When your lens cannot fully correct for a variety of reasons, you're going to get a fuzzy image because they're not converging. We got some nice pictures of that that'll help make that a little bit more clear. I am not going to test you all on all this idea of how an eye actually does it. This is a lot of just kind of fun facts for you all. The thing that I would test you here was that question that I've asked a million times. What kind of lens is your eye? It's a converging lens. Great. So this lens is the thing that adjusts. Your cornea does most of the work, but the lens does the fine-tuning to make it in focus. Your eye cannot focus on things at multiple distances. If you look at someone, I mean, I can see you all in the back room. If you look at someone's back of the head that's close to you, someone that's farther away will be out of focus. Things at the same distance can be in focus because your eye is calibrated for that, something at that distance. Anything farther, out of focus. Anything closer, out of focus. Your all's cameras are the same way. Now you may think to yourself, but I take pictures and everything is nice and crisp. Today's cameras are really sophisticated in terms of what they do. They don't take one picture. And they don't even have one camera. Your camera on here is one lens, just like your eyeball is, unless you have 5 different cameras. At which point, Your phone takes many pictures. It changes its focal distance just like your lens. Imagine your eyeball taking like a bajillion pictures in a split second, combining them all together, and then and that way you get a picture where everything's in focus because it literally took a ton of pictures and combined them all together. So your camera does some really fancy stuff that your eyeball can't. You know, our eyeballs are super cool, but technology is a little bit better in some ways. You know, who knows? Maybe one day you can replace it with a camera. Wouldn't that be fun? I don't know. Maybe that's exciting to you. I don't know how I feel about it. So, as far as correcting vision, we have myopia. I'm not going to quiz you on this, so don't worry about not knowing what the word. Maybe you all probably know this word better than I do. So, myopia is nearsightedness. This is when. Nearsightedness means you can see things that are near, you cannot see things that are far away. And then you have hyperopia, which means farsightedness, which means you can see things that are far, you can't see things that are near. Again, you all can find pictures of the prior here. But we have some nice pictures here that you may not have seen, maybe you have seen, where you see what happens for nearsightedness. So nearsightedness is when you have something far away. When something is far away, it's as if those light rays are parallel. Why? Because the thing is so far away, like I can't even draw it off the screen, that if I drew my rays, they effectively are going to be parallel. Do you get, let's take an example of the sun. The sun is emitting light rays everywhere. If you get far enough away, two light rays are going to be pretty much parallel to each other. You get far enough away from something, two light rays that are small angle will basically be parallel. So things far away, those light rays are parallel. Bam, bam. When things are closer, we start to see the images that we've been drawing so far. And so if we look at the far one, light rays are parallel. We want this to be back here, but it's not. You can see here it's focusing that light too closely. Too closely. We need that focus to be back here, where the actual sensors are. And there's two reasons this can happen. If your lens is too strong, it's converging those rays too strongly before it should. Those light rays are getting converged before they should. They should be converging back here, but they're converging up here, and that's bad. Or if your eyeball is too long, literally too long, it thinks that the sensors are here, but in reality they're back here, and it's not adjusting it correctly for whatever reason. All right, so that's one case. Then we have hyperopia, which is the farsightedness. So if we have our object right here, we again want to focus at the back of the eye, but instead it's focusing behind the eye. Those light rays are converging behind where the eye sensors are. And that can happen for the exact opposite reasons. Its lens is too weak, it's not focusing enough, or your eye is too short, at which point it thinks at the back of your case by case. What kind of lens do you all think we need to correct nearsightedness, where my light rays are converging before they should? I can see things close, but things far away, my light rays are converging too closely. Everything that's far away is blurry. This is what most people have, myself included. I can see things close perfectly fine. I cannot see things at a certain distance. My eye doesn't do what it should be doing, and they're blurry. Why does my eye in particular do it? I have no idea, but it does. Maybe I should ask my optometrist. Maybe they can figure that out. Next time you all go to the eye doctor, you can maybe ask him if you're nearsighted or farsighted, hey, why do I need these? Because they're looking into your eye. I'm sure they could tell you, oh, your lens is blah, blah, blah. You know the science, so you can actually converse with them about that. They do love talking about that kind of stuff. At least mine did. All right, so our rays are converging before they should. What kind of lens should we use to fix this? I'll go up to 1 minute and 20, so we'll go 20 more seconds. And 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. So the key to this problem is looking at the next slide, which has the answer, or just thinking through it. So the next slide, I already got kind of a picture that shows it, and I purposely have this because it'd be harder for me to draw. If they're converging too soon, why don't we just spread them out a bit? That way, and we have a nice picture here that shows it. you're going to use a diverging lens. Why? That diverging lens will spread them out, so now they'll converge a little bit later on where we want them to converge. Now the light rays will actually converge a little bit later. Previously, they were converging here, and that was bad. But if we spread them out a bit, now they'll, they start out a little bit more spread, and they'll come back together right where we want them to. So, the answer here is a diverging lens. Hey, good job. And if you have farsightedness like myself, that's what your lenses are doing. Now, the question comes, contact lenses don't look like, no one's contact lenses hopefully look like this. That's the clever thing with contact lenses, is they've managed to take something that is curved like this and make it behave like this. Now, there's creative ways they can do that. They can make it kind of thicker and thinner in some ways, but because that lens, that contact lens, is so close to your eye, they don't need to make that big of differences in the plastic itself or whatever the material is that these are made of to accomplish that. So my guess is that if we looked at a contact lens under a microscope or something, I don't know if this is true, fact check it for yourself, is that it would kind of be thinner in the middle. So if I have, here's a contact lens that we would expect, maybe it's a little thinner here in the middle. The plastic is a little thinner there, and so you get this concave lens kind of there. But you all can't tell because it's so microscopically tiny. They don't need to make that many big adjustments because it's literally on the surface of your eye, so a tiny adjustment makes a big difference. That's my guess. I haven't looked into it. Fun thing for you all to look into. Hey, do you physically care about 3 about that? All right. If the light is converging after the back of your eye, what kind of lens will we use instead? So, as all of us, hopefully, God willing, get older and get real old and our eyes start to crap out, I think many people, I don't know, again, this is speaking from a physicist who knows almost nothing about medical stuff. When you get older, people tend to develop farsightedness. Don't quote me because I'm basing that on literally, I've seen a lot of older people wear glasses. So, and they've said that, and I don't know. This happens, and you have to have a different type of lens to accomplish it, which kind of gives me the answer. We'll go to a minute and 10. What kind of lens will help fix this problem? So one day I will be so blessed to have both of these problems and then need both of these lenses. What a joy. Or just get laser eye surgery. And 5, 4, 3, 2, 1. So again, pro tip, check the next slide. The converging lens, if they were converging too late, well, let's just move those light rays a little bit closer together, and then they'll converge where they should. Before, they were converging back here, so why don't we just move those light rays a little bit closer with that converging lens so that they converge where they should, and then all is well in the world. All right, so we are moving pretty quick. Like you all can see, we actually don't have that much left. Pretty much after this is going to be the math, so I'm going to introduce the equations today, kind of talk to you a little bit, and then Thursday we'll be finishing it. Let me give the answer here. Good job, it's the other one. So, we've been just conceptually talking about this. We talked about magnification. I gave an equation to that, pretty straightforward. Here's the equation that we're going to be using for the rest of this PowerPoint slide. It's basically the main one from this. It's a fairly straightforward equation. 1 over the object distance plus 1 over the image distance equals 1 over the focal point. 3 variables, object distance, image distance, and focal point. Distance of the object is distance from the lens of the object. Fairly straightforward. Just measure it, it's done. Distance of the image, we have some rules that we need to do. And you'll end up finding this when you calculate it. You'll end up finding these values. You're going to find that the image distance is negative if you're on the same side as the object. This happens in a converging lens if your distance to your object is also the focal point, and it happens always in a diverging lens. So let's just quickly draw a picture of this. If my object is here, and my image is here, and let's just draw a diverging lens, because it always happens for a diverging lens. So say you draw all those beautiful rays, or you do the math. This is when it's going to be negative. The distance of the image here will be negative. The beautiful thing is that'll come out in the math. When you're solving the problem, you will get a negative answer. That's not something you chuck in at the end. That's something that will come out as the math. If I start with a positive object distance, and now let's go ahead. So if you're on the opposite side of the lens, your image is positive value. So if I am on, let's take a converging lens. Here's my object. Here's my image. This image distance is going to be positive. Again, that will come out in the math. How does that come out in the math? This is the one that basically you all need to remember, and it's super easy. There's no caveats to this. F is the distance from the lens to the focal point. And if it's a converging lens, it's positive. If it's a diverging lens, it's negative. Always. So whenever you are doing the math, if I give you a converging lens, you need to put the focal point in as a positive number. If I give you a diverging lens, and I say, hey, here's the focal distance, when you use this equation, you need to put it in as a negative number. Okay? If you can remember this rule, this just comes out in the math. The distance of the image, that one with the slight, not terrible rules, but it's got a little bit more caveat to it. That's kind of harder to remember. The bottom one's much easier. Converging lens positive, diverging lens negative for focal point. Distance of the image, you got to just remember that diverging lens, it's always negative. Converging lens depends where you're at, depends where your object's at, and that will come out. I keep saying it again and again and again because it will happen. All right, so we'll do just like one or two more problems. We'll probably even do these problems again next time, just to maybe I'll remake similar ones to kind of test this. So, great, now I've got my ghost images. Wonderful. Let me save this, close it, reopen it so we don't have our ghosts following us along. They probably went away anyway. So the first question is, yeah, all this. An object is located at 2 meters. If the magnitude of the focal point is 1 meter, what is the image distance if the lens is a converging lens? An object is located at 2 meters. If the magnitude of the focal point is 1 meter, what is the image distance if the lens is a converging lens? All right, we'll go to 135 on this, so 15 more seconds or so. All right, and 5, 4, 3, 2, 1. All right, so our object distance is always positive, always. So let's write down our givens. Our object distance is 2 meters. That's always positive. Who cares what kind of lens you have? Our focal point is at 1 meter, and it's a converging lens. So it's positive. Converging lens, positive. Diverging lens, negative. Great. We're solving for the image distance, and I just gave you the equation for that. 1 over f equals 1 over di plus 1 over do. I'm going to go ahead and do the algebra here with the actual variables in it. So I'm solving for di. So I'm going to kick that 1 over do over. So 1 over di equals 1 over f minus 1 over do. Just subtracted it over. And if I want to get di by itself, it's on the bottom. So how do I get it to the top? I do 1 divided by everything. Do 1 divided by everything. So if I want di by itself, it's going to be 1 over f minus 1 over do. And this is something for every variable. If I say find the focal point, find the object distance, find the image distance, basically at the end of the day, it's always going to be 1 over either you're adding or subtracting depending upon the problem. 1 over 1 minus 1 over other, 1 over that plus that. And step 4, just plug and chug. So di equals 1 over 1 minus, so really the big mistake here is if you forget to do 1 over or if you mess up the subtraction. 1/2, which equals 1 over 1/2, which equals 2. Behold, my answer was positive. I told you it would. It comes out in the math. You don't assign positives and negatives at the end. The answer you get is the answer. There's no assigning positive and negatives at the end. If your answer is positive, it's positive. If your answer is negative, it's negative. You do the assigning at the beginning. And really the only assigning here, object distance is always positive, focal point will be negative diverging. Okay, we're going to do this other one later, so let me do a quick wrap up. I will tell you all something. I should have said this at the beginning, but I got so caught up in all the fun things. Your all's final, I've decided will just be 40 questions, multiple choice, that's it. No free response. I don't know if that's better or worse. You all tend to, I think, do better on the multiple choice, just from what I've seen. Couple reasons for that. One is it lets me test a wide variety of things by offering more multiple choice. I get to test a wider variety of stuff, give you a better chance to show your stuff. If you make a silly mistake, it doesn't matter as much. And then 2, I have a handful of days to grade everything afterwards, so this is easy to grade. So, benefits us both, hopefully. 40 questions will be pretty much evenly distributed from every section. So we've talked about 12 topics, 11 or 12 topics. So take 40 questions divided by that. That's how many questions you'll have from each one. So each week of content will, I think we have 11 weeks. Yeah, we've done 11 weeks of content, so take 40 divided by 11. So roughly 4 questions per thing. Maybe someone will have 3 instead of 4. Just like the last time. So yeah, that's that. I will post the solutions to these. I'd say solutions, that stuff like that. The test 2 solutions are posted. I mentioned that before. And I'm going to post your all free response grades tomorrow. The average for those was a 63. That'll get curved up to a 75% as well. Funny how that all worked out. Won't change your all's grade that much, but that will get posted tomorrow. The solution's already all posted, so you can see if you did it right or not. You don't have to wait that long. All right. Have a great, if you have any questions, email me, talk to me. Otherwise, goodbye online people. Sorry for all the difficulties such as technology.